Good morning, everyone. That one was for you, Flavio. I know you're out there. I saw you in the room and just wanted to wake up and start your day with a little of your favorite band. So 10 points if you can name that song. I'm sure he will. But anyway, good morning. My name is Bob Foreman, and welcome to hour one of our mastering the relational ROXIE and regressive realms with ECL redo. So we're gonna run through it again. Those of you that were with me on Tuesday, we had a little technical glitch where we had overloaded the room, and so we have alleviated that situation now. We have two rooms going on. So this is English room 1, and there's an English room 2. We are going to then, with that in mind, I'm going to go ahead with a little bit faster introduction again, because we talked about denormalization already. However, I'm between a rock and the hard place with that because we're also recording this. So I don't want to miss some key information. So we will review some of the stuff that we talked about on Tuesday, but then I'll have more time to focus on some of the things that we did not get to. So with me today is, as always, my colleague, my mentor, my manager, Richard Taylor, who is on board here as well to monitor the public chat for questions. Because of the length of material that's in this session and the length of time that we ask you to place your questions in the public chat room. Richard will be monitoring that, and then he will attempt to answer. Sometimes, like, he was really great during the ROXIE session. I have to give him kudos for that because he was answering questions along the way, which was really kind of great. So thank you again for that, Richard. And thank you for supporting me. And without further ado, let's see here. We have a couple in the public chat already here. What do we have here? Yeah. So Jim DeFavia correctly guessed the bumper music for the workshop. Way to go, Jim. All right. So I'm going to go ahead for more real estate of the slides and stop sharing my webcam. And let's get started with hour 1 of the relational realm, which became hour 3.5. So this is the relational realm of ECL that we're going to be talking about. Once again, the purpose of this workshop was to explore areas of ECL that sometimes the normal developer doesn't go to. They work with data transformation and ingestion and scoring analysis and to some extent converting and joining data sets together. But these are areas that sometimes people don't explore, or they don't have a need for, or for whatever reason. So we're going to be looking at this today, relational data sets, and talk about why they're still important in ECL, the power that you have with them, and how to deal with them, actually work with them in ECL. So those of you that are going to be looking at our source code and might want to try some of the code later on, this again is for your convenience. The URL to our training cluster on the left is how to set it up in the ECL IDE on that server line right there shown with my red dot. And then over here is the launch.json file that you can add this entry to your VS Code IDE. And then also we have PDFs out there that are in English or Portuguese. There's the Portuguese set also out there. If that suits you, you can download that. Plus, there's a mod file for those of you using the ECL IDE for an easy import of our source code. And there's also a zip file that's out there for those of you using VS Code. So once again, we are talking about the people, property, and tax data files to start this relational realm. They're all flat fixed length files that I've previously sprayed. They are all related together. People has an ID field that links to a person ID field in the property data set. And the property data set also links to the tax data set via a property ID. So in summary, we have a parent-child-grandchild relationship here that we are going to explore. So on the Tuesday presentation, I started talking about denormalization. And denormalization, in summary, quickly, is just putting relational information into the same record structure. And I'll say that again. Denormalization is the process of putting relational information into the same record structure. So we've got parent information here, people and vehicles that are related to that person. We have property information that's related to that person and tax data that's related to each individual bit of property. So this is a contiguous record structure that goes from start to finish, from the start of the record to the end of the record, and all parent and child information are then in scope. Relational data also implies implicit grouping of the child data, which we're going to be talking about shortly. Again, this is how we deal with things in our everyday LexisNexis cluster. We have our data in a normalized format. So usually we have our header file. This is called the data donut. We have our header file in the center that has a Lex ID that links to a variety of these different entities out here. So you can have a person header file that links to their vehicles that they own, properties that they own, any legal filings, email addresses, etc., etc. All right, so let's take a look at, first of all, working with child data sets, which we call adding the data set field into a record structure. Then we're going to be talking about, again, the transform and denormalize. And I'm going through this a lot faster than I did on Tuesday, but we still need to review this and talk about this. This is a standard normalized record and data set structure. Those of you new to ECL then know that when you spray the file to the cluster, there's 3 steps that need to be done. You have to first get the file from the outside world to the cluster. Secondly, you have to shape your data using the record structure, define how you want to deal with it. In other words, this record structure could be 155 bytes long, and you could just define one field that says line. But if you know more about the individual information, then you can split it up into smaller pieces and then analyze it more effectively and more visually. So once again, HPCC, we like to say it has an open data model. This is a flat file as well with the designation of Thor. Now, nested child data sets, well, we just changed the narrative a little bit by adding the child record directly to the parent record structure via a data set statement. The data set statement says we have a data set here of records that adhere to the child record format. We're limiting the child records to a maximum count here of 20. Studying this slide, you see that the parent file is actually a list of addresses, and then the child records are people that live in that particular address. And you see the link field here then would be the address ID in the child record to the ID of the parent record. Once again, the file itself doesn't really indicate that it's denormalized. All of the denormalization that you can detect and recognize is actually discovered in the record structures. So then we talked about how to denormalize the ECL way, and we started with a review of a transform structure, which this is the basis of transforming data. This came about probably in the 3rd or 4th year of the ECL cycle. We came out with a whole suite of transform functions that were built to extend the power of ECL and provide different scenarios for different types of transformation, whether the transformation might involve deduping, sometimes the transformation might involve pairs of records, sometimes the transformation would involve more than one data set, like in a join. But in this example, we're going to be looking at the denormalize statement, which is, again, a specialized form of a join. The first parameter, parent output, the second parameter, the child record. And the parent output of denormalize is the original parent record with additional fields that make room for the children. So these additional fields, if you have a fixed amount of child records per parent, then you could just add additional fields to that parent record structure. But if the child records are variable in number per parent, like one parent could have 3 child records, another parent might have 4 child records, another parent might have none. So you can add to your record structure, the parent output, the nested child data set, which allows variable child records to the parent record structure. So we have our parent output, the child record set, the join condition that links parent and child together, And then the transform passes the left record, which is the parent, which has room for the children, and the right record set, which is the actual child record structure itself. An optional counter, which is very handy, that will keep track of the number of child records that are added to each parent. So here is our example of a simple denormalize that had a fixed amount of child records. So in this example, we did not need to use a nested child data set because the number of child records was fixed, 2 child records per parent. So in this example here, we just have a cval2_1 and a cval2_2. And the first step in denormalization, as I talked about on Tuesday, was to make room for the children. So in this example, a simple table will suffice. We can read the original parent file, output to the new output record here, my output record, which will then build the parent record plus the 2 additional fields that make room for the children. Once we have the parent record with room for the children, now we can go ahead and denormalize it. So we take the output of this table, which is p_records. We have the child file coming in, the condition here, which is a left value 1 and a right value 1. The denorm of the denormalize function has a left and right, which is required. We pass it an optional counter. In this example, the counter is being used to detect which one of the child records is being processed. Remember, we have 2 child records per parent. So if the counter is 1, we're going to move the right value, which is passed by the child file, over to left.cval2_1. And then as the counter goes to 2, it's going to then pass it the right value to left.cval2_2. With that in mind, remember, denormalize is also persistent. In other words, as long as this condition is true, the left record stays persistent in memory and the right record is changing as it goes from iteration to iteration. All right, this was our visualization of the denormalize that we just looked at. And now let's take a look at the nested child example. Now, this is the example that you'll have a different number of child records per parent. In this example, you see Hugo, who has 1 address linked by this name ID. Eliana has 2 addresses in this child file. Mr. Anywhere has 4 addresses in this file. Mr. Nobody, looking at the number 3 here, there is no child record with the number 3. So Mr. Nobody has no child records. So step number 1, we define a nested child data set here that, again, consumes or references the child record here with a name ID and an address information. We give it a name. You can call this anything you want. We're calling it children. And we're setting our maximum count to 5. Once again, the rules for denormalization doesn't change. Rule number 1 is make room for the children. In this case, instead of using table, it's a lot easier to use project. Because project, we can, again, input the names table, which was our parent file here. The output is our denormalized record structure, shown again at the top. And we use an empty set syntax here, close up on self.children, and an empty set syntax, which is very handy if your child record has 30 or 40 different fields. You're making room for the children within a nested child data set. You don't want to have to say each individual field in the transform, initialize all the numerics to 0, initialize all the strings to blank. This statement does it with just 1 empty set. The empty set then signals that any numeric fields in this child record structure will be 0. Any string values will be set to blank. And then we do a self is defined as left, which moves all the parent fields over from the project over to the output of the transform. And this gives us room for the children now. So we have a parent file with an empty nested child record ready to be added. And then finally, we then go in and we denormalize. And denormalize, we denormalize the result of the project, which was called p-table. Once again, the child record normalized addresses. Then we have our link field, which is a left.nameID to a right.nameID. we call denormalizing, which is a left, right, and then pass it a counter. All right, so those two examples I just demonstrated are shown in the ECL repository, so you can go back and study them, run them, and please give us a shout if you have any questions. All right, so this is the part right here where we got to the point where we had to end our workshop on Tuesday. So everything from this point on, we were just finishing up talking about DWR relate. So I'm going to go ahead and take us now into the ECL IDE. All right, so the ECL IDE should be popping up in your workshop room window. I can see mine. And from this point right now, let's take a look at the code. Now, remember, the relational realms, the regression realm, the ROXIE realm, this mod file moved the individual code examples into separate folders. So we're going to be focusing today on the relational folder. And once again, the input data that we have right here is, well, we start with people. And people has an ID field right here that refers to property using the person ID. And then the property ID that's in property is linked to the property ID in the tax data file. So these three files are normalized right now. We're going to relate them all together. And step number one is to shape your denormalized records, make room for the children. So in this file right here called file_people all, it's a module. I've got a number of exports in here. I am adding my denormalized records into this people all because, again, people all will be the result of my denormalization. So we're going to denormalize in two steps. The first step we're going to denormalize is property and taxes. And then we're going to take the result of property and taxes and denormalize it with people. So there's two nested child data sets that are going to be added to our final output here in this workshop file. The property, the first nested child data set is using tax data, and straightforward. It's just the tax data layout that's added here. And in our training data, we're assigning a maximum of 20 tax data records per property. And then the second phase of our denormalization will take the output of this layout property tax, and that will become the child record for people. Notice we also add a counter field using an unsigned one to count the number of child records per parent. You don't have to do that, but it's just a very convenient thing to add to your denormalized output. So once again, we have here the relation BWR_relate. Step number one is to denormalize property and tax data. And so once again, step number one, make room for the children. So we're going to read the property file. We're going to output to our prop tax layout, which is simplified and referenced here. And we're just calling it prop tax. This is a local definition, which makes my code easier to read. So prop tax is the record output. We're clearing out the tax records to numerics to 0 and strings to blank, moving all the property data over, and that will give us a prop parent result. That prop parent result gets applied to denormalize as the left record. The right record is the child record tax data. We denormalize it, and this is critical right here. Very important, everyone. Focus on this line. Self.taxrex is defined as the left.taxrex plus the right record. So remember I said denormalize. As long as this condition is true, the left record remains persistent in memory so that on each iteration, it takes the result that's already in the left record and it's appending the new right record that we are passing to the transform. So that's denormalization of property and taxes. And then we go into phase 2, which is the denormalization of that property taxes with people. So once again, the structure is still the same, where we're reading the original people file. We're outputting to that record structure called people all, which now has property and tax data as the nested child data set. We're initializing that nested child data set to an empty set. So the same process, make room for the children. The denormalization happens here. We're linking the ID to the person ID. Persisting the results. So if I run this again and again and again, notice I ran it this morning just to give myself a quick test at the bottom here with syntax errors, and the persist file was up to date, so it just sped up my denormalization process. Here's the result of BWR relate. And so you see here, this was just property and tax information. If you scroll to the right, you'll see that the IDE references the child data in the form of XML. Since this is a .NET list control, that's the best it can do. But we can actually see the full rendering of the parent and child information by simply clicking on this blue link at the top that says View Nested Embedded Dataset in the ECL Watch. When I click on that, we immediately go to the outputs, and we can verify that the people and property and tax data look like they've been denormalized properly. And what I mean by that is there's no distortion in the data. And you can see here I've got a property count of 6, and I can scroll down here and count 6 properties for Petronica Spock. And each one of her properties has tax data information. Like here's a tax count of 6, and we have 1, 2, 3, 4, 5, 6 tax data records. And that's how easy it is to denormalize your data. So this is the point where we actually had to terminate our workshop. I'm going to stop sharing now. And now let's talk about what was the advantage of doing what we just did. Once you denormalize a data set, 2 rules come into play called, and this is part of something called implicit dataset relationality in nested child datasets. Rule number 1 is that your parent record fields are always in memory when operating at the level of the child records. And then rule number 2, when you reference a parent record, only the child records that are related to that parent are now in scope. So what happens during the denormalization is you have implicit grouping. And what this means is that some ECL statements that are not supported, like global dedupes, for example, are not supported normally using group dedupe with all. With a denormalized data set, you can easily use that now because of the child's implicit grouping per parent. So what do we do with this data set relationality now? What is the reason for denormalizing? Now, there's 2 reasons for denormalizing data. Number 1 is because your vendor, your customer would like it in that format. And yes, someone sent me an email just last night. They said, can we despray denormalized data to a landing zone? And the answer is certainly yes. So you can take the denormalized data that is stored on the cluster, and then you can actually despray it back out to the landing zone, and then you have your parent-child relationships in any file format, by the way, flat file, CSV file, XML file, or JSON file. So that's the first reason, is that sometimes your customer requires your data in denormalized format. And sometimes you get the data in denormalized format and have to normalize it. We're going to talk about that in just a minute. But here we have the other reason. The other reason is that analysis of these relational data sets become more robust and a lot easier to implement when you're studying the relationship of child records to parent records. For example, in this data set that I'm going to be working with, I want to know more about the people. What kind of people am I dealing with here? I think there's 279,000 records in this people data set. I want to know about these people. So I want to know about their property. And I want to know specifically in query number 1 here, how many properties have or have ever had 3 or more bedrooms. So there's an exported definition here called prop tax beds 3. We have to filter both property and tax data. And so there's also a little best practice hint here to create a simple function to eliminate redundant code. And then the ability to test this query on the level of the parent. So here's the reference to people, and here's the reference to the query that we're going to be discussing. And all we want to know is, does this person have at least one property record that had bedrooms that were 3 or more? So greater than 0 will give me my accurate people count. Now, I started with this query because not all of these relational queries have to be difficult. This query, as a matter of fact, is pretty simple. And you see here, all we're doing is we have this local function called is greater than or equal to. And the reason we did that was to eliminate some of the parenthetical things that are going on here, because we're doing a count of property, and property is doing a filter, and inside that filter we have another exists and another record set with another filter going on. So what's going on here in this particular count of property? Your two friends, your two functions that are going to be critical in the working with denormalized data sets is the exists function, number 1, and then we're going to talk about another function called evaluate. Well, we'll talk about exists first. Exists simply looks at this record structure and record set, record set, and if one or more records is true, then exists will return a true. If the tax data record fails, then exists will return a false, and then, of course, then the count is going to be strictly dependent on property, because this is an or condition. So if property has 3 or more bedrooms, or if any tax data record related to property has 3 or more bedrooms, then let's go ahead and count the record. All right. So we're going to be taking a look at that in the IDE. Now, my colleague Hugo, who is in room number 2 right now, Hugo wanted to show the difficulty of running a simple query like this that just has one line of code with property and tax data exists, because this is the relational data set that we created, denormalized data set. And Hugo wanted to say, well, what would I have to do the same kind of count using normalized data? So this example right here, which is also in your repository, is providing the same property count from the standpoint of using normalized data. And notice he's using a dedupe with a group or dedupe with a sort as equivalent. And then he's doing a count of a join and full outer join. So he's got a lot more going on here. And he's not even including how do you count the people now. So if you count the people, you're going to have to add another join. So right now we were just on the level of counting the property and showing the equivalent of using a normalized code versus using denormalized code. When we look at the graph of this, which is kind of interesting, you'll notice that the normalized code is actually slower than the denormalized code. So the denormalized work unit took about 1 second, and the normalized code actually doubled. So once again, working with denormalized data sets is actually more efficient when you're doing query analysis. All right, so the first example I'm going to show you real quick. I think what I'm going to do, I think probably the best thing to do is to talk about these queries, and then we can examine them all in the ECL IDE. The second query that we're exploring and demonstrating in this workshop is called prop val small street. This is one of my favorites, and I have a lot of reasons for telling you this is one of my favorites. The specification is to calculate aggregate property values for properties on small streets. And those small streets are courts, lanes, ways, circles, places, or trails. Now, the interesting thing about this is Richard Taylor, many, many, many years ago, with another gentleman, Tony Middleton, when they were putting this training together, they actually went out and they talked to the development teams that were in the trenches working with real data. And this property data that you're seeing in this example, this training data, was actually real properties, but we pulled and scrambled the address information to remove the PII information. And he tried to find out like what were like real world problems that you would run into on a day-to-day basis. We had a list of them, and then we came up with 9 queries that we use in our advanced ECL class that go from the very simple to the very not simple. So this is one that was just one of my favorites, because not only does it look for small streets, but then it says use either the total or the assessed value as your aggregate property value. If there's no properties, return a -9. If there's no street properties, return a -9. And if there's no street properties with no valid values, return a -9. Otherwise, return the aggregate property value. So we've got an if condition that's somewhere in here. We're going to return the aggregate property value, or we're going to return a -9. So again, some people read this and they go, why am I doing this? What's the reason of -9? -9 was a kind of a throwback to the mainframe days, that if there was a field or a record that was marked invalid, they would stamp it with a -9 code. So we're just kind of using that as an old stamp there. Plus, it's a negative number, which it's very unique and easy to filter on too. If I want to know all the people that don't live on small streets, once I get my query result, I can simply filter on -9 and easily get my count. So this query again comes a little bit more involved than the previous one, query number 1. We're just simplifying the links to the roots with property and total value and assessed value. We are looking in a Boolean definition here for only small streets that match, and I have this Boolean definition called is small streets. Then this one always gives us discussion in the classroom. We're looking for either a valid total amount or assessed amount. Now, valid amount and valid year, which is in another query, are helper functions that are in the repository. And a valid amount says, I think it's greater than 0 and less than 999,998 or something. So if the amount of the field that we're testing here falls within that range, then we call it a valid amount. So if total's true or assessed is true, then we have to make a decision. And in the if condition, the second parameter of if is always your true value. So if both of these are true, if total and assessed are true, then we just look for the greater of the two. If total is greater than assessed, grab the total. If assessed is greater, grab assessed. But if one of these fails, which means either total is invalid or assessed is invalid, then we drop down to our false condition and say, well, if total's valid, then that means that assessed might have been the one that threw us out, so let's grab total and use that one. Otherwise, if total is not valid, well, then let's assume assessed just for the moment. And then down here in the small properties definition, we now combine the small street filter with the high value calculation and test that assessed one more time. Make sure that high value is valid. If it's valid, let's count the property. So if we do have small properties, we take the sum of the small properties of the high value, whether that be total or assessed, whichever one we chose. And if there are no small properties on the level of a person, then we're going to return a -9. All right, I think it's time. I want to show you something in the IDE right now. I'm going to go back to my screen real quickly, and we'll share this IDE. Okay, and now the first query that we were discussing in the slides is shown right here. So it's the exact same code. The small street code is shown right here. And now, how do I evaluate this? If I ran this from the level of this code right here, it would be reading it on the level of property. And that's not what we really want. We want to count the persons who have property living on small streets. We don't want all the properties with small streets. That's going to give us an inflated count. as if we were going to run this one on the level of, and that's the normalized one, this is the denormalized one. If we ran this one on the level of property, it would also give us a count of all properties of bedrooms greater than 3. We don't want that. We want people. So here's the way that I test these queries through this little BWR file that's also included in the repository. So the first query, once again, greater than 0, prop value small street greater than 0, and there's a third one that I'm going to discuss in just a moment. And also, I have another statement here that now starts to make sense about that val small street, where it had, if no properties are valid on the small street, or no assessed valid or total value is valid, then return a -9. If I put this query in scope with the people record set, then watch what happens. So in this people output here, there's Petronica Spock again. This is the denormalized output. Here are the 3 queries that we've demonstrated in this workshop. So Petronica Spock does have properties on a small street. Kim Demirtas does not. Delin Malsh does not, and so on. For the tax beds, we can see Petronica Spock has 5 properties that have 3 or more bedrooms out of her 6. Kim Demirtas has 1. Delin Malsh has 1, and so on. So the queries come to life when you can include them in line with your denormalized data set, and we're actually adding value to this original record set. By now we know people that live on a small street, we simply filter out the people that have the -9 code. We could then filter on prop tax beds, looking for people with 6 beds and 5 beds and just 1 bed. So it becomes very powerful analysis tool. And here I just have a quick validation of my counts. So the first query had almost everybody had 3 or more bedrooms. The second one, people on a small street. And the third one we haven't even looked at yet, but we will. But again, we're counting on the level of people. So out of 279,000 records, 265,000 had 3 or more bedrooms. A good number of people live on small streets. What can you assume about these people now? You can start, and more of these queries, you start to build a model of who these people are. And there's one query that we do about people that own trucks. So we say, all right, how many people own trucks? We pull the vehicle data set in and we denormalize that. And then we look at people in vehicles and say, if they own a truck, are they more, what kind of person would own a truck? Are they more agricultural? Are they just own a truck just because they like to drive trucks, or they help their friends move every week? I don't know. So again, you could tell more information by building more and more queries. So the last query that we're talking about here is drilling down to the tax data information. And real quickly, I'll go over this because I think we're getting pretty close to time here. Yeah, I've got about 5 minutes left. So this example right here drills down to the tax data information. We want to get the assessed value from a tax data record of the most recent tax year. So we also have to filter on property, and then we use the evaluate function, which is one of the things I was going to talk about. So this code is probably the most complex of the workshop. I've kind of simplified it on this slide, though. It doesn't look that bad once I simplify it on the slide. We're getting the valid year of a property, year acquired. If the year acquired is not valid, then we go with the year built. We look for a value of the property. Once again, we look for total value being valid. If it's not value, then we're valid, then we go with the assessed value. Down here in our properties, we validate it one more time. We make sure that the year we're selecting is valid. We make sure that the value that we're selecting is valid. And we are only interested in properties that are not apartments. We're only interested in homes. We're then going to do a sort by descending year because, again, the idea here is the most recent tax year of the most recent property. If they buy more than one property, then we sort by the highest value. Then we do a filter on our tax data. We make sure that we have a valid tax year. We're only interested in tax data that has a valid tax year and the assessed total value that we're going to be extracting. The most complex thing about this is the evaluate. The evaluate uses a single record, and then based on the values in that single record, you could then drill down and then determine if you have a valid related tax data record to that property record. So as we go in here, we first say, look, if we don't have any properties that match our criteria, return a blank. Then if we do have a valid sorted property, now let's evaluate it, because not exist is false. So that's the value we return first. So then evaluate here, we say, now let's look at the sorted properties first record, which is the most recent year and the highest value in a descending sort. And then we say, okay, if we don't have any tax data record for that particular property, return a blank. If we do, let's go get the assessed total value and let's cast it to a string 8. All right, so that's some of the examples of some of the queries that you can work with in denormalized data sets. And once again, you can take a look at that code. I encourage all of you, the cluster is open until 7 o'clock tonight. Now, I have very little time to talk about normalize, but you don't need to talk about normalize in a lot of time because it is very, very simple to use. The first parameter of normalization is any record set. It doesn't have to be a denormalized record structure. It can be any record set because the second parameter of normalize is a numeric expression. And sometimes people use normalization outside of the box. They'll take a normal record set and they'll do something with it n number of times. All right. And so, but normalize, yes. Normalize, again, is a specialized form of join, again, that it was originally designed to take denormalized record sets and normalize them. And how does that work? Well, the numeric expression tells you how many child records you have per parent. So you can call the transform n number of times and extract the child records based on the number of child records that are specified by the expression. Okay, so here is an example very quickly of a fixed amount of child records. So all they're doing here is they're calling a hard-coded 2 in the normalize, and then they're saying choose. If the count's 1, grab the first denormalized field and put it into the child record result. Otherwise, take the second child field and put it into the child record result. The output record is your actually child record here. And it's kind of side saddling as both here, but we're actually doing both here in that case. So this was a fixed amount of child records, not too exciting to look at. What was more exciting is the variable size of child records, and that's where we're going to end up right now. We're going to take one last look at our nested child example. All right, so our nested child example that we showed in the slide that had, remember, Hugo and Eliana, and we talked about denormalizing and then adding the children and so on. And again, we had a result that looked like this once we denormalized. Now, the normalize, well, you could do it because we were good in our denormalization. And I mean, but we were good. We had a counter field called numRows. So we could use in our normalizing that rows reference. So per parent record that's being read, remember the record set right here, it's going to call this record structure child number of times because this number of rows is storing the number of children. And for Hugo, that number was 1. For Eliana, that number was 2. For Mr. Anywhere, that number was 4. And it's real simple. after we pass this record structure, we simply extract from the nested child data set an index into the nested child data set, this being an index number. So if there's 2 child records, 1 would grab the first child record, 2 would grab the second child record. So normalize will work that way. Normalize can normalize using a numeric counter. Now, sometimes you're going to get data that doesn't have that counter, so you can reference the child record directly. And instead of passing the left with the counter, this is called form number 2 of normalize, where we actually pass it the child record alone. And remember, these are specialized form of joins. So this is the left, this is the right. So when we're saying pass the right, it's passing the nested child data set from the left to the transform. And the transform simply extracts the record, puts it into the child record structure, and you're there. And then even to simplify form number 2 to an extent, here's an inline transform that just simply says transform right. So then I don't need this transform structure. So 3 different outputs here. Child 1, good. Child 2, good. Child 3, good. Uh-oh, what's this one? Norm project. Uh-oh, look at this. Aha. So the child records were extracted not once, not twice, not 3 times, but not even a 4th time using, well, here's the big surprise. Here's the big reveal, gentlemen, ladies and gentlemen. We have a project here that reads the denormalized records directly as the first parameter, and then simply moves any matching fields from the denormalized record structure to the child record. So this is a new form of project. Well, it's not new anymore. It's been around since HPCC version 4, I think, or maybe even version 3. But this form of project simply has parent as your first parameter, or input record as your first parameter, and then the output record set as your second parameter, and it does field matching. So if you construct your denormalized references correctly, you can reference using project, and this project performs exactly like normalize. And this is the thing of ECL. There's many ways to get something done. There's many ways to accomplish a task. And, you know, often the big question I get from people new to ECL is they go, what's the difference between a table and a project? And essentially, the operation of it, as you all know, is it does the same thing. But there's things that you can do. Project actually stands alone because project was designed to work with relational data sets. If you try to do it with a table, you're going to have all kinds of problems. But a project was built for working with denormalized data sets and relational data sets. And that pretty much brings us to the conclusion of this workshop. I've got about 10 minutes left. So I've gone through a lot of things quickly, and I know that you guys have some questions out there. And so I'm going to enable my webcam right now. We'll go into a quick Q&A mode here.
Hey, Bob.
Yes, sir.
Sudip Kandel wanted to know which IDE version you've been using in the demo.
Wow. All right. In order to use or find whatever version you're looking at, you look at the About icon in there. The version I'm using right now is actually 7.10.24. So I actually grabbed the latest and greatest that was out there. Our cluster is using version 7.6.36. Which was the latest and greatest, I think, AWS version. But I'm using 710.24 right now. And for the most part, it's been pretty solid.
Okay. And Vibod Vanani asks, does denormalization work faster than joins?
Yeah, well, if you have only one join and then you have a denormalize, I mean, denormalize is a specialized form of join. So if you're doing one join to one denormalize, they're probably comparable. They're probably the same. But the issue with joins is that joins works with, if you're using multiple data sets, you're going to have to do multiple joins. And then also if you have a parent-child using a join instead of a denormalize, then the join will have bloating, because the join will just grab one parent, one child, one parent, one child, one parent. So you have duplicate parents. Then you got to go through roll-ups and other things to get your data to what you want. So that was, the advantage of using denormalize is to eliminate the use of multiple joins.
So generally, querying a denormalized data set, in other words, a nested child data set structure, it's going to be faster than doing the same amount of joins, the same thing with joins.
Absolutely correct. Thank you, Richard. Yes.
Thank you for the confirmation. That's all the questions that I saw. Does anybody else have a question? Put it in the, you can, if you don't want to turn your microphone on, you can just type it into the public chat.
You can even ask the monkey.
Oh yeah. Talk to the stuffed animal. Jim DeFabio is typing.
Oh, now we're in trouble. When we have a question from the head of documentation, look out. Is he still typing?
Yeah, he's still typing, and so is Greg Whitaker. So we got a couple of questions coming in.
Greg.
Oh, so Greg's just saying it was a good job, Bob. And
Thanks,
Jim wants to know, can the work unit analyzer detect when you should use denormalize over join? Good question.
That is a good question. And I will have to get back to you on that one, Jim. I assume that by analyzing the work unit, well, it depends. Like when you should use denormalize over join would depend on your nature of your data. I believe. So more of a okay, yeah. So yeah, we'll have to take a look at that. But I think, again, should use denormalize over join. Will it recommend it? That's maybe something to add to the people that are working with the work unit analyzer. I don't know if it's part of it yet, but that's a good suggestion, Jim. Very good.
Yeah, the fact is that it's always how you architect your final solution, how you architect the data for your final solution is highly dependent upon exactly what it is, what problem you're trying to solve, and what data you're trying to deliver. There are instances where a denormalized data set might be faster, but might not serve the purpose of the product that you're trying to create. So doing the joins would be more, better for the product itself. Although if you don't know about using nested child data sets, then you're always probably going to be doing the joins.
Right. The other thing I really like about denormalized data sets in my discovery through the realm was that it worked very well with ROXIE. I was very pleased and surprised that I can create indexes on denormalized data sets, and they rendered very nicely to the output. I think there's a limit to the number of nested, though I have to explore. I remember reading something from Gavin on that. But then also the ability to despray. I had an email from CapelDev last night about that, and the ability to despray the data very easily, and then also work with different data file types. That you can denormalize a CSV file, you can denormalize an XML file, you can denormalize a JSON file. So we don't, the HPCC file formats don't care. You can work with flat files and CSVs and XML and JSON, and do some better analysis of your relational data. So again, going back to that data donut in the first slide, data is related. And if you want to explore those relationships, it's good for analysis to denormalize what you want, and then run through some queries and discover more insight into the people that you're working with.
Very good.
All right, any other questions? Happy Friday, everyone. I want to say that. Thank you for staying with us for the whole week. Again, apologies for Tuesday again, but looks like we regrouped and we were able to accommodate everybody with 2 rooms. I'm a little overwhelmed at the interest that we had. To be honest with you, I didn't expect this. So I'm very humbled and honored to be your instructor for these 3 hours. And, you know, based on the response that we've had and the excitement, please email us. Let us know what you liked and what you didn't like. And then we'll put together some more of these down the road. We'd love to do it. And thank you for your suggestions, and thank you for your questions. And stay well, everybody. Stay well, stay safe, and good luck with all of your ECL projects. And let's enjoy the rest of the show and have a great weekend, everyone. Yes, and the sessions are being recorded, Ross. We do have it. That was one of the blessings of it crashing on Tuesday, was the original plans. So we are, they're all recorded now. They will be available. You'll be able to watch these again. Thank you,
kudos
Oscar.
to Bob. Kudos to Bob. He survived the whole week.
Yeah. Thank you, Rodrigo. Always good to see you. Thanks for joining us. Shijana, thank you very much. Appreciate it. Donald, thank you, Don. Thank you for Donald. Thank you for your suggestions with the ROXIE stuff too. We're going to be working on that too. We'll send a modified code version up there. And thank you again, Jim. All right, guys. We'll see you in the plenary sessions. Thank you so much. Enjoy the rest of your day. I'm going to go ahead and turn off my audio. Thanks again, everyone.